if you start the. Okay. So welcome everybody to the May meeting of the Stockton Astronomical Society. Hi, Christy.
Hi,
How's the ankle?
I can walk and I can drive.
I see you walked in. The best part is you brought the cookies when you walked in.
I do.
Yeah. You guys help yourself to the refreshments courtesy of Christy. We have one announcement to do before we get to our program, to our guest speaker. And as you see here, just recently, the Stockton Astronomical Society was awarded a grant, a $500 grant from the Northrop Grumman Corporation. Courtesy of Michael Warzika's public service that he did related to Stockton Astronomical and also the Sacramento Club, right, Michael?
Yes.
And so Michael's going to tell us a little bit about how that came to be. We're the beneficiaries of that. And so, Michael, tell us what you do for Northrop Grumman. Well, tell us as much as you can.
Okay, sure. Yes, I'm a electromechanical engineer with the Northrop Grumman Company. I work in McClellan, California, which is just north of Sacramento. And our division does electronics work, RF work. Also, we do work in quantum computing, which is pretty cool. And my work is strictly in doing electromechanical design. And that's about all I can say about the work I do.
Okay, and then tell us a little bit about how you came to get the grant from your company and how that worked out.
Sure. Northrop Grumman is really big on public outreach as well as volunteering efforts. And we have a program where we credit hours for volunteers. If you hit 40 hours of volunteer time per year, the company will give a $500 grant to a 501(c)(3) of your choosing. They also have a lottery where every quarter, if you log hours, they will give you a $1,000 grant to the 501(c)(3) of your choosing. Unfortunately, I haven't won that one yet, but last year I did over 40 hours. I do outreach work with Northrop Grumman. We go to schools and do talks about STEM and engineering. I volunteer for SVAS, doing star parties and whatnot. I've given talks to SAS. And I'm also a NASA Solar System Ambassador, where I do public outreach for space flight and astronomy and basic STEM fields. My background is actually, I have a degree in aerospace engineering and mechanical engineering. So aerospace design and aerospace products have been, my heart and soul ever since I was a kid. So I'm really happy with Northrop Grumman having this type of a grant program where we can reward the people that we do outreach with a grant, and hopefully one of these days I'll win that lottery during one of these quarters.
Well, excellent. We are so thankful for all that you've done and what your company's done for us, and so we want to thank you and give you an applause in return.
Thank you, thank you, and it's a real pleasure working with SAS. And I love the fact that you guys have the Telescope Gift Program, that you do outreach in the community. It's a wonderful organization to be a part of, and I'm happy to contribute as much as I can. I live in El Dorado Hills, so I can't make it live frequently, but it's great that I can tie in via the internet.
For sure. Excellent. Again, thank you so much. With that, let me go ahead and ask Eric to do the introduction of our guest speaker tonight. We'll jump right into our program. After our speaker's presentation, then we'll do some question and answer with him. And then we've got some announcements and some group interaction things. So Eric, go ahead.
Okay, welcome everybody. Our speaker today is Antonio Rodriguez. His talk today is going to be titled "The Sun's Story from Birth to Death." And let me tell you a little bit about Antonio. He is a fifth-year PhD student in the astronomy department at Caltech, who is an NSF graduate fellow, also a Ford Foundation predoctoral fellow, and an LSST Discovery Alliance data science fellow. He works on discovering and characterizing treating binary stars from the highly magnetic to the ultra compact and even on stellar mass black holes. His work primarily relies on multi-wavelength cross matches between X-ray, optical, and radio telescope data. A simple tool in the X-ray plus optical sky can efficiently reveal the true demographics of accreting white dwarfs in the solar neighborhood. Antonio is originally from Salinas, California, who completed his undergraduate education in the physics department at Stanford. So everybody, let's welcome Antonio.
Thank you, Eric, and thanks everyone for having me. Let me go ahead and reshare the slides here. Yeah, so fellow Central Northern California resident. Yeah, I wish I could have been there in person, but I actually just defended my PhD this week, so I'm this sort of this awkward limbo where I'm still a student, but I actually do have my PhD now. Otherwise, I would have been very happy to make it and attend your meeting. So I can't quite see the room, but what, how many people are there? I want to get a good sense of, who the audience is. I guess everyone. Okay, great, cool, awesome crowd there. During my talk, feel free to interrupt and ask questions. Like I don't mind that at all, but we can still do like a Q&A session at the end.
There's about 11 or 12 of us here in the room, plus those on Zoom.
11 here.
Great, yes. Yes, I can see you here on Zoom. I guess just to get a sense, I take it all of you have looked through a telescope. Is that correct? Yes. Everyone in the room's looked through a telescope.
Yes.
Awesome. Everyone has an interest in astronomy. Cool. That's great. What's another sort of good gauging question to I see people of all ages there. I see everyone is like under 25, right? So everyone's very young. Everyone yeah, all ages, great. Yeah, there's open up. Yeah, you all look very young. I see just young people in the rooms. This is great. Okay. Great. So let's go ahead and begin. Yeah, so I'll talk to you about the sun story, our nearest star, what we can learn from it. That's the focus of my PhD has been in other sort of more extreme stars, but to understand extreme stars and appreciate why they're so extreme, we really do have to understand the sun and appreciate it for what it is. So yeah, let me talk about sort of the overview of the things that I'll cover in this talk. We'll explore how the sun formed. We'll explore how unique the sun is. This really has deep connections to how unique life might be in the Milky Way and in the universe. Like if our sun is actually very different than a lot of the other stars, that might mean that life requires a sun-like star, which is a very rare star to actually come about. How does the sun even work? I think a lot of people just think it's like a big ball of fire. That's kind of true, but I'll get a little bit more into the subtleties. I want to take a poll here. This is an interactive question. Some people have heard that this is true. Some people have heard that this is not true, but will the sun eventually swallow the earth? Can you raise your hand if you think the sun will swallow the earth? Okay. Yeah. Hope I'm not around when that happens. And then what's left when the sun no longer shines? So I hate to break it to you, but the sun at one point will no longer shine in the way that it currently does. Yeah. Yep. Those are basically the answers, and we'll sort of talk about more sort of more subtle steps that can happen leading up to that. So if there's other questions, ask me anytime, unmute or raise your hand or get my attention somehow. Happy to answer any questions throughout. So solar fact number 1, the sun is a perfect sphere, perfect with an asterisk because it's not quite perfect, but it's certainly better than anything we have on Earth. One way to think about how spherical the sun is to think about its roundness. So what the maximum sort of deviation from roundness you get, you can think of, the highest mountain on Earth, how much that height is with respect to the overall radius of the Earth. So the sun is extremely round. It's actually a really, really good sphere to more than 0.309%. So that's about 1 part in 10,000. Um, Earth is actually not very round. So the sun is already way more round than Earth. Earth is actually what's called an oblate spheroid, and it's actually more elongated at the equator. So you may have heard this, that Mount Everest is actually not the Mount Everest is the tallest peak on Earth, but it's not actually the farthest point from the Earth's center. That place is somewhere in the Andes in South America. So basically, you can see here the sun is way more round than the Earth by many orders of magnitude, by hundreds of times. 333 times, as a matter of fact. So how did the sun form? This is a really interesting story. And maybe you've seen some of these images. Hopefully, one of the great things, I was part of astronomical groups in college and in high school, and something that we really enjoyed doing was just looking at the news and seeing sort of what new images were coming out of new telescopes that were launched. So hopefully you guys saw some of these James Webb images. This one's actually relatively new. Can you raise your hand if you've seen maybe a version, any James Webb image, any James Webb image? Cool, great, that's awesome. So this one in particular, if you zoom in, you can see something really remarkable. So in the left is basically the full image. You can zoom into the square, and then that's the square in the upper right. And then if you zoom in even deeper into that square, then you see this sort of weird, it's like, what does it look like? Can someone describe to me what that shape in the bottom looks like?
A popcorn kernel.
Yeah, oh,
Wow, that's a better answer than I've ever gotten with other people that I've shown this to. Yeah, people say it's like a UFO or like a ring or something like that, but popcorn kernel is great because it's sort of kind of puffy, kind of spread out. Um, it doesn't look like a sphere, right? It doesn't look like just a ball. That's the point. So I'm going to play this movie here, which basically outlines the formation of planets in a protoplanetary disk. And that's the image of what you saw. So first I wanted to show you the real image so that you would believe the simulations that I'm about to show you. So that disk, eventually, basically stars form in huge gas clouds called star-forming regions. You get little pockets where stars can form, and eventually big spheres of gas collapse into a disk like the one you saw before. And then these disks develop rings. And at the very center of those rings is a star. It's a young star that's forming. So all of these rings, you can see they're slowly starting to dissipate, like there's less gas in them. And what actually forms in those rings are planets. One thing that's really interesting about rings in astrophysics is rings are actually very short-lived structures. They're not very stable structures. So in the case of star formation, after only about 1 million years, they start to dissipate and form planets. In the case of Jupiter, for example, Jupiter's rings are also not permanent. Saturn's rings are not like all of our gas giants planets, they all have rings. But most of them will disappear within the next sort of 10 to about 100 million years, which is not very long in astronomical contexts. Yeah.
Tony, what
Yeah, go ahead.
what starts off the rotation of the disk moving like that?
That's a great question. So there's basically the original thing that becomes a star in the star system is a big sphere of gas. And that sphere is about, thinking about our solar system as an example. So our solar system, basically the edge of it extends to where that original sort of cloud was. So that cloud basically made it 3 times the orbit of Pluto. So way past anything that we think is sort of, in the solar system. And the thing is that when you have such a big cloud, it's very easy that if you have just a little bit of rotation in one direction, everything is bound gravitationally. So if even some of the particles start rotating, they'll drag other particles along with them. The whole gas cloud starts to rotate. And during this whole process, mass is sort of falling in toward the center of gravity, toward the center of mass. And as more things sort of fall in, you still have something spinning. And eventually the whole thing gets more compact. And in physics, this is called conservation of angular momentum. If you start spinning something that's very big, even if you spin it very slowly, once it gets small, then that becomes really, really fast spinning. So it's basically the product of distance and basically the frequency of the spin that's conserved. So in the case of an example that you may have seen could be, let me think of sort of more common example. If you basically spin, and you can do this experiment actually, you're spinning on one of those chairs, one of those swivel chairs, and you have your arms out. Oh, you see this with like ballerinas a lot actually. So they basically have their arms out and they're spinning kind of slowly. As they draw their arms in, they spin very quickly. And it doesn't take a lot of initial spin to really get going. That's exactly what's happening in this process of star formation.
Basically, you just need 50.001% of the material mass going in a certain direction, and eventually everything falls in. Because if it doesn't follow along, it gets booted somewhere.
Exactly. And yeah, once you start to have everything just falling in the center, the whole dimensions of everything just shrinks and this spin just gets out of control. And that's how you have these rings and planets forming. Yeah. So yeah, that's a great question. And that very sort of general ideas like that come up all the time in different areas of astrophysics, galaxy formation, right? Even the interiors of stars, that matters. The environments around black holes and white dwarf stars, like what I've studied in my PhD, that all of that basically translates. So it's it pays off to really understand some concepts quite deeply.
Thank you.
And just to, yeah, go ahead.
No, I said thank you.
Oh yeah, no problem. So just to get a better sense, I mean, I think as astronomers, we have this sense of we know that millions of years is not that long. We try to tell people that, we try to sort of tell the public this, but a good way to think about it is, I mean, everyone studies dinosaurs in elementary school. Everyone has a sense of, how long the dinosaurs lived for. We have a sense of how long sort of humans have been around. And we know that humans lived, much less time or occupied much less of Earth's time than dinosaurs. 10 million years, that's how big it is on basically the time scale of the Earth. So much smaller than the entire duration of dinosaurs roaming the Earth. So it's really a fast process, just sort of a different way of visualizing it. Okay, let's move on to the next question. So is the sun unique? No, it's the sun is actually not as common in the Milky Way and in the universe as we thought. It's actually pretty unique. So solar fact number 2 is that the sun's actually a bit heavy. It's gotta watch its weight, basically. This plot is hopefully a plot that you can understand regardless of your math background. On this axis, you can see it's just mass. And this is mass in terms of solar masses, so relative to the sun. And then on this axis here, it's the occurrence. So how common is a star with that mass? So what this plot basically shows is that, the lowest mass stars here at 0.07 solar masses are not very common, or sorry, they're still pretty common, but not the most common. As you move to the right, it's actually stars with about 2/10 of the mass of the sun that are the most common in the universe. And these are about 10 times, about 10 times more common than the sun. So the sun's all the way here at 1 solar mass. And actually, if you get to more and more massive stars, they're less and less common in the Milky Way and in the universe. So the sun's a little bit odd. Like there exists all of these low mass stars, red dwarfs, that are much, much more common than the sun, tens of times more common than the sun. And solar fact number 3, which also sort of relates to how unique the sun is a bit lonely. So this plot has sort of slightly different, like don't pay attention to what it says on this axis. This axis is again mass of a star in solar masses. So the mass of the sun here, 10 times the mass of the sun, 20 times the mass of the sun, 30 times the mass of the sun. And the numbers here on this axis tell you how many companions on average that star has. And by companions, I mean other companion stars. So the fact that there's a half here says that half of sun-like stars, half of solar mass stars, actually have a binary companion. I didn't know that before I started my basically my studies in physics and astronomy. It's actually kind of weird that our sun doesn't have a companion. And if you keep going up in mass, it's remarkable because when you get to 30 solar masses, the norm is that stars come in triples. They have 2 companions, so it's literally 3 stars. So if that's one thing that I think Star Wars got really wrong. Like Tatooine is the only one that has 2 suns, right? If they had made that movie better, they would have shown more stars having more planets having an additional sun. Yeah, so this is actually what half of the stars, half of the planets around sun-like stars. This is what they would see.
Have you had any luck finding other siblings of our sun yet? I know they're searching for ones with the same chemical percentages and so forth that came from the same nebula that we came from.
Oh yeah, so that's actually we have a really good sense of what stars in the solar neighborhood came from the same original nebula and original basically open cluster. So it went from nebula to an open cluster and then basically off into separate stars. So yeah, we have a pretty good sense of that. In terms of whether the sun could have had another companion in its formation, or whether it's like some people still think there might be some very massive cold planet very far away that could effectively be a solar companion. I think there's enough evidence to show that if there is something there, it's actually pretty low mass, and there isn't effectively another star-like companion. But yeah, I mean, most of the stars in the solar neighborhood, we now have such good measurements of their velocities that we can trace them all back to basically the same general vicinity, billions of years in the past. Yeah, so how does the sun work, right? We've been talking about the sun for quite a bit here. The sun is basically like an onion. It has a core, which is very hot. It then has a radiative zone. And radiation is basically just material. It's just energy basically streaming out through material. And then you get the convection zone, which is just like boiling water. You get these moving motions in the boiling water. That's what convection is. And then you have the solar atmosphere, which is here on the outside. And the solar atmosphere is a really, really strange place because the farther you get from the sun, the hotter you get, which makes no sense. This is actually one of the classical unsolved problems in astrophysics. And for the most part, I'd say it's still unsolved. There's like a good idea of what might cause the solar corona, the outermost layer, to reach 1 million degrees. Some version of plasma waves. So you can have waves basically transport energy and heat all the way out to the corona. That's the best idea, but it's not a completely solved picture yet. So yeah, this cartoon here basically shows these various methods of heat transfer. Radiation is just basically traveling through the air, the heat from the bottom of the stove here, and then eventually reaches the tea kettle. And then the kettle has these convective motions basically in the interior, bringing the water up and down. So solar fact number 4, which also relates to how the sun works, starting up the sun, like starting the chemical reactions that power the sun, is actually a miracle. So we've probably all heard some version of, okay, our sun is powered by hydrogen fusion. Hydrogen atoms merge into helium, that generates heat, generates light, and then we get energy from the sun. What's really remarkable is this initial reaction of getting 2 hydrogen atoms, and they're not just hydrogen atoms, they have an additional electron. So it's chemical name is H minus. It's 1 proton and 2 electrons. And what you're seeing here on the left is the initial reaction of something that's called a PP chain in the sun. And if you just have 2 of these hydrogen atoms, the probability that they'll actually come together and fuse is so rare that on average, we'd expect one to happen once every billion years. So that's insane. Like that just goes to show how much hydrogen there is in the sun for these reactions to actually occur in a way that's steady so that we actually get energy from the sun. The sun is basically too big to fail. That's the way to think about it. All these other reactions then are a lot more common. So it takes 1 second for that reaction from hydrogen to helium to then occur, 1 million years for helium to keep merging into basically more massive helium. And this squiggly line is photons. It's light coming from these reactions. But the original reaction that starts up the sun is very tricky to get started just from principles of quantum mechanics. Okay, so the moment we've all been waiting for, will the sun swallow the Earth? Let's see what this will look like. So it is true that the sun will inflate. The sun eventually runs out of hydrogen, so then has to start fusing helium, then carbon, then oxygen. And all of those reactions beyond hydrogen are much less efficient and they're much more violent. So because they're much more violent, they have the effect of basically puffing up the sun. They're less efficient, so the sun is cooler. The sun actually becomes redder. It's cooler, and it swells up and becomes a red giant. And this animation basically shows that that the Earth has no hope, that it'll be swallowed by the sun.
How far along the fusion process will it go? Will it get to silicon or not with 1 solar mass?
Yeah, 1 solar mass, you will get some. Basically, the final reaction is carbon, nitrogen, and oxygen.
Yeah.
Yeah, those will be the dominant 3 elements that just keep fusing.
It's probably not gonna happen.
Yeah, there will be some. There already is some, but it's a very, 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 very small amount.
It's not that's when it just basically quits at that point. Okay.
Yep, exactly. So the short answer is yes, the sun will swallow the Earth. It seems pretty likely. And this is in about 5 billion years. So one of my colleagues, actually, he was a fellow PhD student here at Caltech. He graduated 4 years ago. He discovered the first ever example of a star swallowing a planet. And this was basically the cover of the magazine of Nature that he published that work in. And basically the main point of evidence that he did very extensive work with his group, but the main evidence was a star was quite dim, but very red, so it appeared to be like a red giant, and then it brightened dramatically after about 20 years of some activity. Sorry, about 10 years of having some activity, and then it fizzled away. So it had some eruption, it had some explosion, but it wasn't a true explosion. Like it wasn't energetic enough to be anything else that we know of. The model that made the most sense to explain the observations was actually a star very much like the sun swallowing the planet whole. But we have about 5 billion years for this to happen, so it's all good. Yeah, so this is just sort of a summary of what I just mentioned. You have a main sequence star, runs out of hydrogen, forms a helium core, and then it becomes a red giant. So in many ways, the sun is actually like oatmeal overflow. Like literally, if you leave oatmeal too much in the microwave, what happens is that you run out of water, you run out of the things that you can freely basically freely excite. So then you start to heat up the water that's trapped within the oatmeal kernels. So the effect of that is that those then swell up and the whole thing just gets out of control. So when you run out of the stable, uh, uh, basically the stable fuel, which in the case of the sun is hydrogen, then you have to go to the unstable fuel, which is helium and then carbon, nitrogen, and oxygen. When I first gave this talk, I actually had to overflow oatmeal for the purposes of making this photo. So I had to sacrifice my breakfast. Okay, so how will the sun live its final days? I think this is really where things get quite extreme. So yeah, the sun will actually become a planetary nebula. The name planetary nebula, if you've given basically, any sort of stargazing night to the public, that's one of the questions they always have when you show them planetary nebula. Why is it called planetary? Like if they're not planets. Right, in the early days of astronomy, people thought they were planets, so they gave them that name, but just fuzzier. But no, so planetary nebulae is, as many of you may know, it's just the late stages of a star like the sun. And it's a very peaceful death, actually. They very gently sort of dissipate their outer layers. And all these colors here are basically the result of all of this fusion process of getting hydrogen and helium and carbon, nitrogen, oxygen, all of those basically coming together and then exiting the star. So planetary nebulae are really interesting. They have, I hope you show the public all these, all the ones that are up in the night sky when they're available, but they take on all sorts of different shapes. Some of them are very spherical. Some of them are actually not very spherical. Like take a look at the one in the bottom left and the bottom center. Can anyone guess why they actually don't seem that spherical and they have like a different type of symmetry? Like, why do you think they look kind of elongated in that sense? Any guesses?
Another star near them.
Yeah, exactly. So that was originally one of the ways that people started to suspect, okay, a lot of sun-like stars must actually have a binary companion. A lot of planetary nebulae are not spherical. They're actually quite elongated. So there has to be some other star sort of perturbing the gas, perturbing the motion of everything, that causes this sort of, but there still should be some symmetry, right? So that you can only get from another star orbiting it, not just some star passing by or planets passing by or whatever. Like it has to be something stable in an orbit. So yeah, we think that all that, and we have seen evidence that a lot of those do indeed have another companion in there, another binary star.
Can I add something?
Yeah, of course.
Okay, so like when you're in an airplane and you stall and the airplane fails to lift, one wing always fails a little bit before the other one and it causes it to no longer be level.
is it possible that on a nova, all it takes is just a little difference in the symmetry of the star to make it behave that way?
Oh, for the actual planetary nebula to appear asymmetric.
Yeah.
Yeah, yeah. So at very small levels, that's true. Like right outside of the star, basically, yeah, things will be generally asymmetric. But the main problem with that is that the general environment around the stars, the interstellar medium, is very uniform. So even if you have these sorts of asymmetric outflows or asymmetric layers coming off of the star, it'll mix in with the interstellar medium. And actually, that's what we're seeing here. We're seeing the product of mixed outer layers of the star mixing in with the interstellar medium, and it'll sort of homogenize it and make it appear more spherical. In cases like the one in the upper center, that's kind of blobby, but not quite as elongated. Another idea is that these stars actually have a stronger magnetic field than the sun. So there is some asymmetry on even larger scales that can remain because some of these particles just thread onto the magnetic field.
The speaker
Yeah, go
was
ahead.
that planetary nebulas when they nova, sometimes they're cylindrical shaped. So if you're looking at the end of the cylinder, it looks like a ball. If you look at the side, it looks like a rectangle. Look at it differently, it looks like a bow tie. It could just be from our point of view.
Exactly. Yeah. A lot of them are just because of our point of view. And those that you see like those sort of jet structures from, those are basically jets that come out of the star. And that's also probably due to magnetic fields, we think. So the one in the upper center is actually a really good example. If we did see that one from the sides, from those sort of red structures that you see there, that would appear to be basically more like a circle or a square, because those are jets that are coming out of the side of this planetary nebula. Actually, you can see that in the bottom center one too.
That almost looks like the Saturn nebula.
Yeah. Yeah, no, definitely. And then what's at the center of all these planetary nebulae, and especially when all the gas dissipates, you can see it clearly, is the remnant of sun-like stars, and these are white dwarf stars. I actually did most of my PhD on white dwarf stars, in particular the ones that have a binary companion. So white dwarf stars are basically the same size as the Earth. They're a little bit bigger, but they're about the same size as the Earth. The smallest one that we know of is actually the size of the moon. And white dwarf stars, basically the first one that we knew of is actually a companion to the brightest star that we can see in the sky. Does anyone know what the brightest star is that we can see in the northern sky? Yeah, Sirius. Yeah, so Sirius actually has a companion star. We basically just see Sirius A, which is this one here in the center. But it took to get this image, it actually took the Hubble Space Telescope to zoom in 20,000 times from what we could see just looking out into the sky, to resolve this little guy, which is Sirius B, and that's a white dwarf star. So white dwarfs are basically part of the most extreme family of objects that we know of in the universe, and this family is known as compact objects. A way to basically think about how extreme compact objects are is how quickly you need to be going to escape their gravitational pull from their surface. So for a white dwarf, you literally need to be going 2% the speed of light, which is crazy. Like no spacecraft we have even approaches that. The next sort of system is a neutron star. That's even our sun won't become a neutron star, but more massive stars do become a neutron star. And to escape these from their surface, you have to go half the speed of light, so much, much faster than a white dwarf. And the ultimate sort of compact object is a black hole. And to escape from basically, you can't even really define the surface of a black hole, but you can think of some sort of radius, like we've defined a radius beyond which you just can't escape it. So that's the most extreme version of these objects.
Back to the dwarf. If you've got a one solar mass white dwarf, which is no longer fusing, but it's hot. In a big round billion years, how long before it becomes a red dwarf, and then how long before it becomes a brown dwarf?
Yeah, so white dwarfs actually don't become a red dwarf or a brown dwarf or anything else. White dwarfs are very, very, very slow at cooling. You can think of them as like if you have embers left over from a fire,
Right.
from like a campfire or something. So what they will become is what's called a black dwarf, where there's nothing else left. Like it's just a completely cooled white dwarf. The oldest, so basically the oldest white dwarf that we have in the universe is about the age of the universe, which is about 13 billion years. And even that star has only cooled to 4,000 degrees Kelvin. So it takes much, 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 like hundreds of billions of years to get down to sort of
years before they cool enough to become, so that they're cool enough that they're not throwing off white light. Okay.
exactly. Yeah, it's a very slow process. Yeah. Yeah, so this actually is it's the end of my talk. So this is the final solar fact. Yeah, thank you for your attention. I'm happy to take any more questions.
I have a question.
Yeah, go for it.
This is Eric. Um, when our sun does become a planetary nebula, about how long will it remain in that planetary nebula stage? Is there any idea to know how long that would take?
Most stars like the sun are in that stage for about 10 to 100 million years as well. Um, because the sun doesn't have, so the effect of having a binary companion too is that it typically ejects out. It helps in ejecting out some of the outer layers because it has a gravitational pull on more of the material, and it can basically speed up the planetary nebula process. So the sun, 50 to 100 million years, will remain a planetary nebula.
And going back to the slide, you don't have to go back to the slide, but where you were talking about the inflation of the sun swelling up and into the orbit of Earth. Will our sun, or I guess more generally speaking, any star, can it inflate more than once?
Yeah, that's a great question. And the answer is definitely not the sun, because the sun is not massive enough. After two solar masses, stars that have twice the mass of the sun, they basically undergo more phases of this. So they first develop a helium core, and they swell up to become a red giant. When that happens, they start fuse. So by that point, the helium gets from the core out into the outer shells. And there's still enough mass that the star really, really, really tries to fuse the helium. So it shrinks back down again dramatically. That's called a helium flash, when you start having some helium fuse in the outer layers. And it's probably one of the most interesting pieces of nuclear astrophysics to simulate. People have really tried doing that for decades now, and people think that sort of process lasts maybe like less than a year, which in these timescales is ridiculously fast. So we haven't seen any star actually do that. So it comes back down to the point where it now has carbon and oxygen and nitrogen in its core. And then there's another process called the triple alpha process, which then tries to, after it's fused that, which swells it up again. And that can become a red supergiant. So it's cool because it expands, comes back down, expands again. 2 solar masses and above.
With one solar mass, you're not gonna get a CNO flash, an expansion with that?
You won't get a helium flash. You'll get a little bit of the CNO cycle in this red giant phase, but that's it.
Okay. Alright. Just one with the helium, flash, and then that's it.
Yeah, yeah. So the sun itself won't have a helium flash. It'll try to fuse some of the helium in its outer layers, but there won't be enough mass to actually do that. So at that point, the outer layers just start to dissipate.
Okay. So we won't get the helium flash, it'll just, well, what's causing the expansion then? I thought the first expansion would be because of the helium starting to fuse in the outer core and throwing everything out, and then once it throws everything out, it cools and then collapses again.
Yeah, I guess the subtlety is that the sun will fuse helium in its core, but not in its outer layers. So
Okay. So
it'll fuse it in its core, but it's not enough to keep all the outer layers together.
Okay. So then just whatever is close enough for gravity to collapse, it collapses and there's not enough mass left to do the next chain.
Exactly. It's literally all dictated by how much initial mass a star has.
And how much it retains after that helium collapse. Yeah.
Right.
Antonio,
Oh, sorry, go ahead.
oh, go ahead.
I was gonna see if you happen to know, back on that image where you were showing Sirius and its very small companion. What made scientists even think that there was a companion to try and zoom in that much to find that small companion? Did they just happen to find that accidentally, or did they think, oh, there must already be a companion, let's go look for it?
It was a really interesting story because so Sirius itself was very similar to another star called 40 Eridani B. 40 Eridani B and Sirius were discovered around the same time to have sort of weird motions. This is in the late 1800s. By that point, that was well past Kepler, well past Brahe, like enough astronomers had gotten data across the years for how stars move. And if you have a star on its own moving, as Earth keeps revolving around the sun, as the sun keeps going around the galaxy, it'll more or less follow a straight line, just due to its motion in the galaxy. What they noticed in Sirius and this other star, 40 Eridani B, is that they were moving in a straight line, but kind of doing loops, kind of doing small loops, or what appear to be small loops. This is just based on having really accurate positions to the star. So they figured something has to be creating these loops. They said it was angels at the time, but they figured out, it's actually some other star. It wasn't until this wasn't the discovery of the binary companion. This is just a really nice sort of image that very clearly shows it. But in the early 1910s is when the companion Sirius B was discovered, and that was the first one that was actually recognized to be a white dwarf.
Thank you.
Yeah, no problem.
Antonio, I've heard that there's different generations of stars. So do we know if our sun was created from the original hydrogen that was from the Big Bang or from later generation?
That's a great question. Yeah, and they have these names that are in backwards order. So we're actually a population 1 star. There's then population 2 stars, which are closer to the start of the universe, which are closer to the Big Bang. And then the very first ones are population 3 stars. We're pretty confident that we've seen a lot of population 2 stars, and they're completely different from the sun. So we're very clearly a population 1 star. We're sort of the newest type of star. And that's because the population 2 stars don't have as many metals, don't have as many heavy elements polluted into their atmospheres. Because if you go back to the very first stars, the population 3 stars, when the universe formed, there was basically just hydrogen. So stars could get very, very massive. And once all of those stars exploded in supernovae, then they polluted the universe with carbon, nitrogen, oxygen, all the way up to iron. Population 2 stars, then if you look at them, they have a bit more iron, a bit more of those heavy elements. And our sun is actually very, very iron rich compared to the sort of the average type of star. And even based on where it is within its orbit in the Milky Way, we know that our sun is actually part of this newest generation. I mean, the sun's been around for a long time, right? 5 billion years, but it's just that the older stars, just the population 2 and 3, yeah, they just survived for very little time, less than 1 billion years.
So what are we gonna call the ones that are forming right now? -1 zero?
I know, like where do you where do you go?
Zero?
I mean, I mean, we realize that's not a very good name, not a very good naming convention. So that's typically like everything now is just population of 1. Primarily because we've created most of the metals that we can through stars. So the stars now are pretty different. Sorry, they're pretty similar, the ones forming now, to the sun. You just don't have that much more metal creation than you had before, because you don't have any of the very massive stars actually blowing up as supernovae as you did in the past.
We still have, 20, 30, 40 solar mass stars at Carina and so forth that are going, that should have a higher percentage of iron and so forth in them.
Totally, yeah, but it's just not the same as it was back in the day. It was just every star at the start of the universe. Like, it's the complete opposite of the plot I showed before, where let me go back to it.
Right.
Like this, the slope was the other way around. Like every star was massive, so that has huge effects, where they just pollute everything with the heavy metals, and you simply don't get that now.
Yeah. Well, excellent. Any other questions or comments about the presentation? Any questions? Any more questions for Antonio?
Actually, I have one more question.
Yeah,
So what's your doctorate thesis on?
Yeah, of course. Oh, what was my thesis on? Yeah. It was basically on white dwarf stars and stellar mass black holes in binary in binary orbits. They all have a binary companion. One of the big questions was we were seeing a lot of these white dwarf stars have magnetic fields 1 billion times stronger than the sun. So that's insane, like 1 billion times stronger. We can't create any of that on Earth. And the biggest question is, how did those stars get their magnetic fields? One of the things that I answered in my thesis work was actually they form those magnetic fields through a process very similar to the Earth's magnetic field, basically fluid spinning around in the interior. So yeah, that's what I did.
These white dwarfs have a inner core that's turning at a different rate, has heavier, like iron or something like that, more iron. Okay.
Yep, it's a carbon oxygen interior core, and then there's a carbon oxygen fluid as well that's also spinning at a different rate.
You might find this interesting. A couple of years ago, Mike and I had an observing project where we looked at 40 Eridanus B and the pup on Sirius. So we've seen those 2 white dwarfs. There's one in the southern hemisphere that we can't see from here. Other than those 3, I don't know of any that we could find. I don't consider center stars of planetary nebulas white dwarfs because they're not white dwarfs yet.
Exactly.
So those are the only 3 I know of. Are there any others that amateurs like us can nail?
Like any others, you mean any other white dwarfs in binaries in a similar configuration to like where you see one big bright star and then, you know, the white dwarf that you can resolve next to it? Is that what you mean?
Any other that we can see, period, because right at the moment, those are the only three I know that amateur telescopes can hit.
Oh, yeah. No, there's more that you can get. Yeah, and in particular, a lot of the ones that you can see are the systems that I studied, because those are called cataclysmic variables. They have this binary companion that they gain mass from, and that has an effect of actually lighting up the whole system more. So the brightest one, if you guys can manage this, you might have to take a very long exposure, but the brightest one of those is 8th magnitude in the northern hemisphere.
Well, I'm talking visual. We have 32 inch scopes, so we've seen 40 Eridanus B, and we've seen the pup. And there's one on the southern hemisphere that we can't get from here. I know of no other visual white dwarf that we can get.
Okay, got it. Fair. Yeah. So when if you just visual, you know, anything 4th magnitude and lower, there aren't any others.
Okay, so we've done it.
Yep, you got them all.
That is depressing.
I know. Yeah. I mean,
This
look
telescope,
for the ones that have a binary companion. There's going to be one that will explode, that will erupt. Basically, it'll undergo a nova anytime now. Forget its name. It's exploding soon.
yeah.
T-core boar.
Oh, yeah. Well, this scope's too heavy to go to the southern hemisphere with, so we're
Yep.
out. Now, have you seen these visually yourself?
So all of these systems that I've worked on have all been with you know, with very big telescopes and basically just getting some imaging, but also some spectroscopy of them. So some of these get really, really, really faint, all the way down to like 21st magnitude. Yeah, so I've seen them and have images of them, and basically that's what I've worked on. But yeah, I mean, you're right. There's just so few. Like the nearest one, Sirius B, you can't that, you know, yeah, they have to be the nearest ones for you to see them visually. So all of these are much, much farther away.
I think they're special to observe visually because when you look at all the stars that you can see in a telescope, they're the only two that are not fusing. They're the only two that are the size of the Earth. And they're the two most unique stars we've ever observed visually. But you really need to see more.
It's a really nice way to put it that way. Yeah, it's really special that, yeah, with our own eye, we can see such extreme things. I like that a lot.
Actually, it needs to be different terminology for them because they're no longer stars. Same thing with neutron. So no longer neutron stars are not actually stars because the definition is fusing.
I hate the fact that they keep saying that the central stars and planetary nebulas are white dwarfs, and they're not. They're going to become white dwarfs, but right at the moment, they're 10,000 times brighter than a white dwarf. So people lie to themselves saying, I've seen a white dwarf.
Yeah, no, that's fair. I think that's why I like that family of compact objects classification for white dwarfs, neutron stars, and black holes. Yeah, because they're not fusing. They're not stars in the way that we think of them.
Oh, Antonio, excellent presentation. And by the way, my oatmeal usually turns out the same way.
Fair enough. Yep.
Yeah.
I
Well-
have another question.
Go ahead, Jeff.
We started asking questions, and now Tim's wrapping up. Were you actually done?
Oh, he was, yeah.
I was done. I mentioned, yeah, that was the end of the
Okay.
slideshow. Yep.
I thought we were cutting you off, giving you the
No. No. Well, Antonio, excellent work and best of luck with your continuing research and work on your PhD. Important work, and we would love to stay in contact with you and maybe follow up with you again in the future. So thank you for your presentation.
Yeah, happy to do so. Thank you for having me. Feel free to reach out. Yes, I've got to sign off now, but it was great seeing everyone, meeting all of you. Yeah, keep doing what you're doing. Keep doing awesome stuff.
Visit us sometime.
Definitely.
Thank you. Thank you.
Thank you.
Appreciate it.
Good night.
Eric, thanks for another excellent speaker and presentation.
Hey, welcome.
Thanks for all the IT you were doing here. Thanks for that. You're the man.
Yeah.
I feel like
It
I
went
actually-
by really, it seemed like it went by really quick.
Yeah.
It's been an hour.
It's really good. Okay, so we have a few announcements. Meanwhile, sneak over there and get some of those good cookies. I can see them from here. Look. Our upcoming SAS events, kind of all the normal stuff with the star parties. We're entering into some really good weather windows to where our star parties, Highway 4 and then high altitude look real promising. So I think the road to Peddler Hill by now is probably accessible. So let's look to try to get up there May 24th, you guys. Yeah, try to stay up late. I mean, sleep in that morning. May 31st, we're out at Oak Grove. We've been having a good time out at Oak Grove, huh? Good
Oh, yeah.
turnout, great public. We're kind of tapering off on the amount of stuff we can see, but then that just forces us to look for other things like clusters and nebulas if the planets aren't out. So
It's galaxy time.
galaxy season, right? True. Summer triangle. I'm gonna skip on down to the bottom part because those two star parties are in May. I guess the Girl Scouts really isn't a school star party, but the Girl Scouts are going to have a camp out May 16th out at Oak Grove. That's a Friday night.
No
Next.
move. We need to get a couple of volunteers or else I've got to contact them tomorrow and tell them it's a no-go.
Yeah, so
I think I can make that one.
What's that?
I think I can make that one.
You want to do it?
I can do that one.
Eric, I'm a maybe. Anybody else willing to come out? Shoot out there with your scope?
Yes, I'd be there, but I got a hot date with my wife.
Yeah.
They do it your birthday.
Yes, I can do the,
Okay, then I will contact them. Then what I'm gonna do is, you have the contact info I gave you.
Yes,
Do you want to email it to Eric and?
I'll do that. I'll be the liaison with them,
Okay.
the Girl Scouts.
Do you know how many are planned?
Doug said he
Is
thought
that
about
one troop?
16 of them, 2 troops, which I don't know how many's in a troop for girls.
You guys can decide, we can start early and just do some basic astronomy 101.
Yeah.
Um,
Is the park expecting us?
I don't think so. But I don't think it really makes that much difference. They do not lock the gate when the Girl Scouts are there.
Oh, okay.
So this park will already basically be open. So you won't need the key or anything else like that. Is all you guys.
There used to be a code.
So what you guys are gonna do is they're gonna close the gates at sunset. Okay, but they're not gonna lock them. They're just gonna
Straight
latch
lock them, yeah.
them. So when you guys leave, all you gotta do is unlatch them and then, relatch the thing, but don't, you don't need to.
But we ourselves shouldn't lock it.
What's that?
We ourselves, when we leave, should not lock it though, right?
No, you should
Okay.
not lock it because they do not lock the gates when they're in there.
Okay, and then coming up May 22nd, the Delta Charter School in Tracy has invited us to a school star party.
Tracy, Jeff did it last year or year before
Is that
last.
the New Jerusalem thing?
Yep,
Yeah.
yeah. So we need a couple scopes. I can do that one. But we need at least 2 other scopes out there on the 22nd, so I can.
Give yourself an extra half an hour to find it.
Well, it won't this time, will it? Yeah, that's why you need to let me know that you guys, who's coming out, because it's a little difficult to find.
That's a Thursday? Yeah.
Even with good instructions, it's hard.
Even with the instructions, actually, what I should do is just give you the GPS coordinates.
Yeah,
That's the easiest way to do it.
find it, route finding. Okay, yeah, get in touch with Doug if you're able to join them at the Delta Charter School. Okay, June 12th, we're back here for our general meeting. The speaker that spoke to us in March, I think it was, Richard Stember, NASA Solar Ambassador, is going to talk to us about the commercialization of space. So I'm looking forward to that presentation. June 21st, Highway 4, and June 28th, Astronomy in the Park. So put those dates on your calendars, look them up on the SAS calendars on the website.
June 28 is also.
Yeah.
Oh, I missed that. Okay.
It's what? Sorry.
What happens because we can't do June, we can't do July 5th out at the park. Or nobody really wants to.
Yeah. So Jeff's been doing a good job about sending out emails to the group to notify us of before the star party. So hopefully we can get the, we can man both events. So
I'll be
the photo here is from Eric of the Polaris flare. So Eric, tell us what the heck is a Polaris flare?
Sure, I can probably show you a different photo. Similar one. A little bit more vibrant.
Yeah.
So this is the Polaris flare. So this is in the constellation Cepheus. Polaris, sorry, this flare, I actually don't know why it's called a flare, but this is called a nebula. It's a type of nebula called an IFN, integrated flux nebula. It's very similar to like a reflection nebula. But the difference is like a reflection nebula is reflecting light from a nearby star. Supposedly, IFNs are reflecting light from the entire Milky Way galaxy itself. And the combined light from the galaxy is what's lighting up.
So rather than a bunch of stars, just a bunch of stars.
Yep, exactly.
The whole family. Is that Polaris?
Yep. Cool. And I kind of zoom in here a little bit. I was curious what this was in this.
Focus?
I don't think so, because I saw it in other people's images.
Yeah.
So I'm not sure what is going on here, but it's not unique to mine.
It might be another nebula.
Huh. But it's emitting light.
Yeah. So
It's starting to form a planetary disk.
Yeah.
so
You may have discovered something.
So it's about 783 light years away. It's about 164 light years in diameter across. And it's about 720 by 420 arc minutes in size. So
We had Mel Bartels give a talk on drawing IFNs.
Yeah.
So this is the thing that he draws.
yeah.
How he sees it is beyond.
I mean, yeah.
They're dim. The dimmest.
Were you using filters on your camera?
No.
This is without, so we could see this visually.
No.
I mean, we could image it. We could image it.
Yeah, this was
If your
Image-
eyeball
it
was
was-
as big as.
it was imaged for roughly 3.3 hours
Oh,
at 20, no, I don't know, at 30-second subprime intervals.
Yeah.
So
okay.
and then stacked.
When Mel was drawing these and put them in, the first thing I said was, "You liar."
Yeah.
And
Where'd you come?
I don't know how, you can't do this in California. You just, you have to be somewhere
Yeah.
black.
Really dark skies.
I was at the Campo Seco site when I took this. I wasn't up at Peddler or the heliport,
But not visually.
not visual.
Yeah.
Yeah, great image. Thanks, Eric.
With the C Star, Eric? Was that with the C?
Those was with a Canon 60D8,
Okay,
the DSLR,
yeah, okay.
just mounted on a tracking tripod.
You know those little weird things in the stars, can you zoom on them again? I think that's mechanical, I think that's a mechanical artifact, is it oriented the same way? And there's, can
Yeah.
you go down here a little bit?
In the lower left.
It's also oriented that way.
Yeah.
I think there's something, artifact, mechanical optical artifact of some kind.
Could be.
Go image it again and we'll compare. Yeah, Starship.
Shall,
See if it goes the other way.
shall I show you a recent sun image since we were talking about the sun?
Sure.
Yeah.
Oh,
Yeah.
wow.
So this was an image with my new 76 millimeter Helio star from Skywatcher. And then
Please show me how to do that sometime.
yeah, sure. And then I colorized it.
That's wild.
And then I have an inverted one. I like the inverted
I do
ones.
too.
I think you can see, like, I think it's clear that you can see this
Oh,
arcing
just cover it more.
this far. A little easier. And then I colorize that one.
That's what Antonio was talking about. Nice. Okay, so those are our upcoming events for the next 2 months, May and June. Next slide, please, Eric. So raise your hand or stand up if you've been out to a public star party in the last month or so. You guys have, look at it. Yeah, because hey, we've been having a good time. Yeah. I don't know what Jerry's looking at in the daylight there, but they found something in the scope. The moon, yeah. Yeah, we had a good group out there. So thank you all for coming out. Really?
Annabelle, she was at Delta the night before.
Did you get the hook on her and reel her in? Well, I think she.
Her dad may or may not, her dad's a professor at, math professor at Delta.
Oh, is that who she is? She came to my scope and I couldn't get rid of her.
He was like that at Delta.
Yeah.
I just gave her my scope. At Delta, so there was a miscommunication with Yatsik at Delta, last Friday. He had thought that because of the low turnout before, that we should just call it. And I said, well, that's your call, but I'm gonna wait to hear from you, and I didn't hear from him, so we went out. And we put it in the call out to the other professors and so forth. So it was just his friend there for the math, and Annabelle showed up there.
Darren, I think was his name.
So Annabelle
Darren.
really wanted to see, so I set up my scope and set the chair there and showed her how to work the paddles and the telrad, and so she went at it.
Oh, great, great. No, those are fun times with the public like that. So thank you all for coming out. Next slide, please, Eric. So the Villalobos Elementary School invited Pat to come give a presentation, and they didn't actually put his name on the marquee. I kind of photoshopped that in for you. But it looks like you were having a good time. So show us what you got from them.
I got thank you letters. And in fact, I'm just gonna showcase a couple. One of them was actually from the principal, which is very nice. This may be worth keeping. This one, it says, thank you for coming out and letting us look through the telescope. I love the experience to look through a big telescope. And I want to join the Stockton.
Ooh.
So where are they?
This one I'll share with you only because I don't know how to take this quite. It says, I like you. And then I think I'm a giant rabbit. But there's lots of hearts on it. And this one, in the event, Jerry, that you actually read this one says, thank you. And in fact, it says, I really loved how I got to look at the moon and Uranus, and also loved seeing the sun through the telescope.
Uh-oh.
He drew a picture of somebody looking through the telescope screaming, ah. Now, this really did concern me because I don't remember doing any of that, but I did also, thankfully he wrote here, I did not go by the way. So he was not there. So I appreciate the thank you letter for someone who wasn't there.
Yeah.
You know what, we really, we were scheduled to be there for an hour. We went an extra 20 minutes because there were a line of people. And, you know, it did work well. And well, I chose not to look at the sun only because I didn't want to encourage those little ones, but you could see the shadow on the ground there. But we had the moon overhead, and you know, I don't think anyone that walked up there had ever looked through a telescope before. I love hearing the first word out of everybody's mouth is wow.
Yes.
Yeah, so, yep.
And
But
I've been doing it
thanks,
for a
that
long
was-
time and it never gets old, does it?
Yeah, good job, Pat. It's rewarding.
Somebody my age looks at the moon and says, yeah, man, I've never looked at that before.
Yeah,
Yeah.
you need some 80-year-olds out there sometimes at the park.
I
that
mean,
just- Yeah,
I'll tell you the truth, when we finished up, so they closed everybody up at 6 o'clock or 7 o'clock. At 7:20, I was ushering the last people through, and then I was there for another 20 minutes with the teachers. Because they didn't get a chance to look, and none of them had ever looked through a telescope.
yeah. Actually, so anyone that's doing a school star party, if I'm not there, because I always tell the person, my contact person, to make sure that all the teachers and the principal and the janitors and so forth come out when the students are done, or even before, and come out and see. And then somebody needs to come out and tell us class is dismissed. So it's one of the things I always tell my school star party.
Good practice.
And that's really nice because it indicates that the teachers, if they did not get to look,
Right.
they were supervising
They're
students.
they're busy, usually busy inside because it's usually a
Yeah.
science night or something like that. So yeah. It's the only.
I know we talked about this years before, but we haven't talked about this recently, unless you have, I just haven't really around to talk about. But when we get a school and there's 3 or 4 teachers who are highly interested, it almost makes sense to do a striking sparks telescope for that site. So that the teachers could have a star party anytime they want with their telescope or whomever kid they got there.
Yeah.
Just an idea.
Yeah, good idea.
Actually, that school in Tracy, that's with Bill Kane, right?
Yeah, okay, they've got.
We've done that like 3 or 4 years in a row, and that might be a good school for that, what you're talking about.
Yeah, he was gonna buy a
They're buying their own scope, so we don't have to give them the scope.
But there are some, like New Jerusalem, they don't have a scope, and they appreciated us.
Yeah.
We gotta give them a scope.
Like I said, they were buying their own scope, and Kay had some money from the district and so forth to put together, and so, yeah, they were gonna just get on their own scope.
Yeah, good suggestion though. Next slide, please, Art.
Yeah.
Okay, the new moon challenge, the sliver moon challenge. Only got 3 photos. Mine, Jeff's upper right-hand corner, and Ray. Ray, you submitted a nice one. Extra credit points for Ray because he labeled it on April 28th. Jeff's a little questionable. There was no horizon. There was no context. I think he got it off the internet or something.
Jeff would never steal something off.
No,
the internet.
no.
Picture taken out my car window.
Mine, I choreographed it so the ducks were flying over at exactly the right time. So extra credit there. So it was,
They look like upside down for us.
yeah, they were flying inverted just for that photo. Yeah. Yeah. It's actually kind of fun because the actual night of the new moon, you couldn't see it. Next evening, just a bare sliver, and you had to catch it right before the moon sets and right after sunset. So it's a little difficult, but it's kind of rewarding. Yeah.
Next one.
Okay. So this month, May 26th at 8:02 p.m. We probably won't see it that night, right? but the next night may be May 27th. So mark that on your calendar. And then June 25th is the next new moon in June. You might grab it that night. Yeah. Yeah, Jeff was looking for the sliver moon before the sunset and extra credit points if you find it while the sun is still up.
I still don't know if I found it big enough to see, and I just was too stupid to locate it.
Mhm.
So I'm sure there'd be more.
But like Jeff and I talked, so, you know, as the sun sets, the moon, if it's a new moon, it's only 13 degrees. It's always exactly 13 degrees after the sun.
It was exactly one day past your moon.
Mhm.
At this time, you was moved the day before, so by the time sunset came around, it was about a 29, 30 hour moon, somewhere in there.
And it also.
So it's about
it also
15 degrees or
It
so.
also matters how far north or south it is from the ecliptic. Is gonna change that.
Right, right. This was north of the ecliptic. Mhm. But you can find a planetarium map and it'll show you right where it's at. So obviously.
Sure.
Anyway, Ray, good job. Jeff, good job. You guys try to find out. I don't know if Casey, she was talking about looking for it. So
That's what she's not here tonight.
Yeah, yeah. Yeah. So, okay. The big challenge is now if we can do it 11 more times for 12 consecutive sightings.
Okay, so this next time around, can you bear with me for like a minute here?
Okay.
The new moon is at 8:00 p.m. Monday night. So 8:00 p.m. Tuesday night, it will be a 24-hour moon. So if I can get out there and nail it at 5 p.m., it'll be a 21-hour moon.
Okay.
That's my goal. To get a skinnier sliver, but it'll be a daylight shot.
It's the astronomy group, so.
Okay, I'm done.
We're good. Next slide, please, Art. Okay, so, you know, we've been kind of rolling out these new challenges, these new games, these new things. So we came up with one. This was Eric's idea, the astronomy target of the month. And so the way this works is every month you go out to a different Target store and you take a picture of it. That's the way it works. That's what you had intended, Eric?
Yeah.
Okay. Yeah, right after sunset. Yeah.
So actually, the idea came from what Skywatcher does. So Skywatcher puts out a target of the month. They got these neat badges, but it's like, here's the target for May. So I was thinking of maybe starting something similar, maybe have two objects, an easy and a more difficult object to find, but do something similar where I would list the information, the constellation, all this good stuff, apparent magnitude, so forth, and kind of just steal the idea from them, but have our own certifications for it. So
And you don't have to image it, right?
You don't
be
have
a
to.
visual.
Yeah, they could be visual. Exactly. But so along those lines and along the certifications, under resources, the very bottom here, there is this new SAS certificate request form. So you come here, you fill this out, name, email, and choose one of the categories here. And on this list is not only the new moon challenge that we were just talking about, but the target of the month. So look for the first targets for June in the June newsletter. But we also have these other certifications. We might change this up a little bit, but we've got some Messier group certifications that you can request, the Mercury 1% Club, and also if you want to get a certificate for your SAS membership anniversary, we got this on here as well. So you can select this, fill out the next group, the next form. So For example, I'll choose target of the month. And here, let me just put in my name. Hit next. Fill out the date that you saw the target of the month. Enter your target that you saw and submit it, and then we'll get a certificate printed up for you. That's a basically similar idea for all the categories. If you want to request a new category that doesn't exist yet, you can click on this one and request something to be added here.
Black hole the most.
Yeah.
Target store in Lathrop.
1992 Quasar.
Okay, so look for that upcoming, the astronomy target of the month.
Oh, this one?
Yeah, so Eric brought this to our attention, that on the SAS website under resources, he's going to show us where to go here in a moment. There's this great book that you could download or just read online that is really, really good. I don't know if you all have seen it yet, but you've got to enter the password, and we'll share with you the secret handshake.
We're
You ask for-
recording right now, so let's not share.
Yeah. You don't want to broadcast across the internet.
We'll let you know what it is though. But yeah, in this book, it's a really good book. It's several years old. To be honest, the reason why it's password protected is because I received it for free. It was downloadable, but I don't know how they feel about sharing it to the whole public. So that's why it's password protected. But it's a really good book. It starts out first talking about an introduction to deep sky object observing, going over quite a bit on the different observing equipment, binoculars, telescopes, eyepieces. It's a pretty thorough book. And then it gets into the constellation guide. Let me drop down.
Yeah, there's pretty complete star maps in here.
Yeah, let me quickly drop down to, I think it's like around page 30 or so. So a good one, especially for newbies. Let's see here. Yeah, it's like this one. So this is a list of the constellations by season. So you can drop down this list. We're in May, June. It gives you the list of the constellations, so you can go right to those sections and take a look at them. And let's see, is it? So the way that it's formatted is it basically starts out. I'm sorry, I'm jumping around. Basically, every constellation starts with this little summary with the name, an overview of the binocular objects and urban objects in the constellation, but it breaks it down by the type. GX is galaxies, OC is open cluster, PN is planetary nebula, gives you the right ascension, declination of the size. The MBUDR here is M is Messier, B is binocular, E is urban, D is deep sky, R is the RASC, the Royal Astronomical Society of Canada, and their catalog. And then it also will give you, like down here, their own little like number of stars. Basically, how easy is this object, or how popular or how bright it is, things like that to determine how many stars it gets. So the more stars, the easier it is. And this is also a difficulty rating here. These little, I don't even know what they are, like little semicircles. But then more of these two indicates how easy it is. But so it does that for every constellation, lists objects from different catalogs, and like Tim said, the maps are pretty good. So let me go down here. Not those. That's what eyepieces is.
Yeah, I had to scroll through to find them
Yeah.
too.
So it gives you a photograph of it, all the objects that it's talking about too. So it gives you like an example of what you could expect to see through your equipment and a map.
That's how Mel sketched him. He
Yeah.
had this book.
Yeah. And so it does that all for all the objects in the constellations that it includes. It's pretty thorough. So it's a handy book too for doing like Disney marathons and whatnot. So anyways, I wanted to make sure, especially for Jinka, we have this free book. Go look it up.
Yeah, thanks for posting that on the website.
It's been there for a while, but we seldom talk about it. It's been on our website for years. While we're talking about the website, I just added in these planetary infos. So if you're volunteering and you want to get a quick fact on one of the planets that are up here, and the moon. The first one here, let me can I zoom in? Oh, here. So this first one is in metric units. Same thing in US units, the next chart, and then this is an Earth comparison chart. So breaking down the differences between all the planets. So it's handy to have out at the park. You want to look up something.
Yeah.
And then the other one that goes along with this is, what's this one? Is the notes. So the different categories that were on that sheet, talking about, the mass, diameter, density, that's all in here as well, if you want more information on how it's determining its numbers. And I guess finally, I want to reiterate that we have a SAS library. The library is at my house. If you click on SAS library, we've got all these books that I cataloged.
I have some more to contribute to your library.
Okay. But if you're interested in checking out any of these books, just contact me, email, phone, and we'll try to arrange like one of our events to bring it by and you can check it out.
Yeah.
Okay, Doug.
A lot of good resources.
Thank you for taking Jerry's load the other day.
So, Doug, come up and join me. This is something that I just heard about, and it's quite alarming. Come up here, Doug. Yeah, because Doug's going to tell us what we should be concerned about.
So I just told Tim that I think everybody should have their helmet, an umbrella, because the sky is going to be falling. This is supposed to be a probe, Russians launched a probe to Venus back in March of '72. And it didn't quite go off as planned. There were some problems with the second stage, and it just kind of fell into Earth orbit. Well, it's been decaying, that orbit's been decaying since 72. And within the next 5 days, I think, they have been down to, it's coming back to Earth somewhere between 52 degrees north and 52 degrees south.
So that's why I put the map there. That's the Canadian border and the tip of South America. They got it narrowed down to.
Yeah, so I just thought that everybody should probably carry an umbrella with them or something like that. So that the thing weighs, when it was launched, it weighed 1,000 kilos, but I think they said that this thing weighs, what's left up there weighs about 500 kilos. And it was designed to, it has a heat shield on it. So because it was designed to land itself on Venus, which has an extremely thick atmosphere. So it's probably a good chunk of it's going to survive Earth. Or
Yeah, it's welded titanium, 300 pounds of welded titanium.
It's good that they narrowed it down to just where people live.
Yeah.
Yeah, just the latitudes.
So I'm laughing at that joke because I can use 1,000 pounds of titanium.
Okay, well, let's see if we can land it there.
So note there It still technically belongs to the Soviet government, which I'm not sure who it does belongs to now.
The land's on my house, can I sue them?
Basically, yeah, you probably could. Good luck with that. And if they want it back, I would say, fine, pay for the damages that it did to my house.
Well, the story I read was this was like 3 of these probes they sent up at the same time. One actually made it to Venus,
Yeah.
right? 2 others, this one and another one, didn't make it.
Right.
The parts landed in New Zealand from the second one.
Yeah.
It landed in a farmer's field. Well, they contacted the Soviet Union, and they denied any knowledge of it, right? So it's not ours. We don't know anything about it. So when it lands in your living room, Jerry, you just got a Christmas present.
Might we need some salt water?
Yeah.
Salt water, yeah. That's
So,
how,
yeah, Soviets spent a lot of time trying to get to Venus.
Yeah.
It's not very friendly. I don't think anything that they landed on Venus lasted more than 20 minutes or so.
Yeah, actually, I read that the first 3 that they thought they were not successful. And that there had been a Russian scientist that had been telling everybody that the surface of Venus after that thick atmosphere and so forth was probably around 900 degrees Fahrenheit. And they thought it was crazy. And they, you're an idiot, forget it. And so the first ones failed. They couldn't figure out why. And then finally somebody went to it and said, well, maybe this guy's right. And a few other people started going, yeah, I think he is right. And they realized that as the landers came in, the circuit boards, all the tin and lead melted right off the circuit boards. And so they couldn't even call home.
Yes.
And so the next one they sent up with, I don't know what they used for solder, but something that would last at not over 900 degrees Fahrenheit. Gee, it phone home.
And all kinds of ideas. One of the scientists that worked on this project for the Soviet Union was Andres Rodriguez, who was one of my instructors at UOP.
Oh, how cool.
Yeah, so he was from Cuba. And so he was a fun guy, but his thermodynamics was his thing. It was his specialty. And that's what he worked on, how to make stuff last on Venus.
Jerry, do you have any sense from him? What was their objective? What were they hoping to actually learn or find?
they had some instrumentation on the probe that they knew was going to only last for a short period of time, but
Yeah.
the probe that did land, they got a little bit of data, right, on the
So they just
Conditions.
atmospheric temperature,
Right.
just
They wanted
basics.
to do something that the US couldn't do.
Okay. Oh, okay.
There was a lot of that.
They did image the surface.
Did
So-
they? Okay.
It's sickly yellow, put black and white picture color on it.
Yeah.
It was pretty nasty.
There's been a couple, the Americans sent a couple of probes to get what little information we do have about Venus. And there's on the books, there is another one going to Venus, but it hasn't been funded or anything else like that as of yet.
I think they've only got, Russians, we've only got one actually landed image though.
But there was more than that.
I heard that too. Only just
Only one? Okay, because I thought there was a couple that.
And what I read was that it's predicted to hit Earth the 9th or 10th. So that's either tomorrow or Saturday.
Right.
Yeah, so yeah.
It's
Anyway,
coming. Thank you.
be safe.
Yeah, you got us worried now.
We're in tinfoil hat.
Yeah, the probability is like 1 in 10 trillion, okay.
Yeah. Okay, and speaking of vehicles, space vehicles that hopefully this one's not falling out of the sky, is the ISS, the space station. And I noticed, I monitor heavens above. You guys probably check once in a while too, don't you?
Yeah.
But the flyovers that are coming in the next 3 days are pretty magnificent. So tonight at 9:40, 21:40, there's a 3.9, a negative 3.9, super bright. And it's going to be really high, up at 81 degrees. So as soon as you get home from the meeting, go out at 9:20, look for it. Another one, minus 3.4, Friday night. And then Saturday, a -2, Sunday, -3. So a lot of good opportunities to check out the ISS. We were up at Highway 4 one time and it flew over and I caught it in my scope. What a thrill that was.
That's great.
Yeah.
He did it as well one time.
Yeah.
With his Dobsonian.
Yeah, with these as high as they are, it seems like we could image them if we had somebody that can.
I turned the link on to the video, then I followed along my finderscope, and then every now and then I had a frame where it was sitting in there. It's pretty
Okay.
awful, but I was able to get
It's
it.
bobbling in and out of frame.
I had maybe 2 frames that were almost clear.
Mhm.
I love the ones that they get with it crossing the sun.
Yeah.
And they'll have this picture of the sun and then there's the black of the
Yeah.
ISS.
Or the moon, yeah.
Or the moon, yeah. It's cool.
Good stuff. Okay, I think we're closing in on the end of the slides. So in the newsletter was the Astro word, little variation of a word scramble. And so you all know I was over at Doug's shop cleaning up the archives. And so I ran across an old newsletter. So I'm flipping through it from March of 2006. In fact, our speaker that month was James Hedrick. Right. So I'm flipping through here and there's a word scramble in here at the back. And so I just reprinted this thing exactly like it was, except the guy that submitted it was Jeff Baldwin. I scratched his name out.
Oh, that's what
And I
that
put
is.
my name in there because you see, he said, okay, this is plagiarism at its worst.
Yeah.
Well, plagiarism at its best is when you copy somebody else's copied work. So that's the story behind.
It's research, it was double layered.
Yeah, I did my research the same way. So, did anybody solve the puzzle?
I did not think of it.
You guys are so lazy.
Oh,
Okay.
Well, as I mentioned my email, I found the word steroid and was wondering what that was.
Yeah. You found one word or partial part of a word. So,
I called him up and said, Ken, no, I emailed and said, because I don't remember.
I can't see anything.
I said, why would you put my name and then cross it out? So he had to tell me the whole story about how I had made this first, I had no memory of doing that.
And then after I was supposed to, then I wrote that $20 from you too.
But it was hilarious. I had no memory of doing that until after I looked at it for a while and go, oh God, yeah, I remember doing that.
okay.
That was hilarious.
And so now your penalty is you've got to submit a new one,
I got one already.
like 19 years later.
I was gonna say, Tim, we could reuse this in 19 years.
Yeah.
Well, I'm the only one that solved it. Yeah.
I'll
I
have
guess
to
we could
cross
use it.
out Tim's name and put in somebody else's.
So,
In many years, you're gonna see a lot of structures.
yeah,
They're on different axes every,
Yeah.
there you go. Actually, it was kind of tough to solve because there's all these words at the bottom that it took me about half an hour over a couple of cups of coffee that Saturdays.
But you got the secret word, right?
I got it, but I'm not telling you.
Okay.
oh, the secret word at the end.
Yeah, when
I
you're
didn't
done,
do
it's
that.
letters left over, it makes a secret word.
Hey, Dennis.
This has nothing to do with anything in particular, but I have all those things that Omar wanted. I never got a phone call from him. Did anyone hear anything?
That all our one.
All the
He's gonna have
the
that-
bookmarks.
The bookmarks, yeah,
Oh,
I told him. So I kept waiting, I figured he'd wait until Wednesday and he never did call.
I should have brought the ones I had tonight, because I've got like.
He had some,
Yeah.
so
He had none, I don't know.
I don't know, but thank you.
For his event.
So I have them sitting on my kitchen table.
Oh, thanks, Dennis. Hang on to them because you'll use them at different public outreach things, so. I think that's the last slide, isn't it?
Memory.
That was last one.
We can't remember Dan's name.
We're a little bit over time, but anybody else, anything we left out or any comments from anybody else? Christy, thank you for the cookies.
Yes.
And thank you, congratulations on your recovery.
And congratulations, Jink, on your striking smart scope.
Yeah, yeah, good work. Okay, we'll see y'all.
Yeah, all right.